There as well, Dr. Joseph Dufek, who has helped a lot getting these simulations running and sort of the work I've been guiding the work I've done as a PhD student at Georgia Tech. All right, so let's see if this guy works. Cool, it works. All right, so volcanic plumes are often highly charged. Maybe the most evident consequence of this are these sort of beautiful displays of lightning that you get in especially during vigorous eruptions. So very energetic eruptions tend to be highly electrified. And you can sort of see from this picture that lightning sort of tends to come in different modalities. So sometimes you have this sort of scattering of little teeny discharges right near the vent of the volcano. Sometimes you have discharges in the middle of the plume. And then you have these huge discharges, kilometer-long discharges that come from the top of the plume all the way to the ground. And so recent observations of volcanic lightning have only happened, or basically any observations have only happened recently, although in the scientific context, I know at least the Greeks knew about lightning, but it was more sort of a curiosity. It wasn't really anything that people really studied until maybe 20 years ago or so, 50 years ago. And what people are beginning to find is that it seems that lightning activity tends to correlate with the dynamics of eruption. So how energetic this thing is, how big it is, how long it lasts. And so because lightning produces a whole array of electromagnetic signals that go from RF to sort of slow varying electric and magnetic fields that you can measure remotely, it opens up the question of whether you can use lightning and charging in general to probe the dynamics of plumes and get at information that otherwise you wouldn't be able to obtain just because of the hazardous nature of the eruption. So for example, in this plot over here, this is lightning data from an eruption in Alaska. The volcano is called Redoubt. And so you can sort of see that at the onset of the eruption starts around here. You have a very high activity of sort of, they call it an RF hum. Basically, a lot of lightning looking like this sort of little small discharges. And as the eruption progresses, namely as you get this big cloud of ash that rises into the atmosphere, lightning strikes become much more discrete. So you can actually begin to see individual lightning strokes. And so this is sort of the first work that suggested that dynamics in lightning is something that you can maybe use to study volcanoes. All right, so how do volcanoes charge? I mean, this is actually one of the problems as to why people haven't studied lightning before. It's because we don't really know how volcanoes charge. We have some ideas, but it's still somewhat obscure. So this is your typical volcanic plume. You have a nice volcano, Mount St. Helens in this case, the 1980 eruption, and a big jet of gas and particles that gets shot up into the atmosphere. So at the very bottom of the volcano, basically where your magma is rising, and the magma is essentially a glass filled with bubbles, and as these bubbles expand, it breaks that glass catastrophically, and so some initial charging or primordial charging might come from the fragmentation of that glass. We call that fragmentation charging. Higher up in the plume, where you start to condense both magmatic water that's in the magma, but also environmental water that's carried up with the updraft, you get charging mechanisms that are similar to those in thunderstorms, so interactions between ice and graupel. Then throughout the entire eruptive system, you have something called triboelectric charging. Triboelectric charging is basically physical or frictional charging as particles collide and rub against each other. And you can subdivide this charging into two modalities. In the lower, hotter regions of the plume, you have silicate-silicate particle collisions, basically just ash grains colliding, and then at the top, you have potentially collisions between ice. So in this talk, I won't address all of the charging mechanisms, but I'll specifically focus on some of the work we've done with silicate-silicate tribocharging. And the main goal of this project is really to create a numerical model where we can take microphysical triboelectric charging relationships and then put them into a large-scale plume, so a simulation of a plume, to see if we can replicate some of the lightning observations that people have done in recent years. Another problem is that tribocharging itself is a poorly understood mechanism. So even though it's maybe the oldest manifestation of electricity known to man, the ancient Greeks knew that if you rub paper against amber, for example, one charged positively and one charged negatively. We still don't really understand it very well. In systems of particles that are composed of two distinct substances, so in this case you have a cat and the other particle phase is polystyrene or packing peanuts. You can maybe describe tribocharging with what's called the triboelectric series. So basically, this is all empirically derived, and it tells you, okay, so if I have one substance, the cat, rubbing against another substance, the polystyrene, the cat, which maybe we could approximate to be rabbit's fur or hair, and the packing peanuts to be polystyrene, well, the rabbit or the cat is going to charge positively, and the packing peanuts are going to be negatively charged. The problem is tribocharging is also observed in systems where you have chemically identical particles, so particles that don't have any chemical differences. And so in the case where you have heterogeneous particles, you might say, okay, well, maybe charging arises from differences in surface work functions, or basically there's a potential when you bring two surfaces together. But in this case, when you have chemically identical particles, you don't have that difference in work function, so you don't have basically a potential to drive charge across. But you observe tribocharging in systems of homogeneous particles, chemically homogeneous particles, all the time. So for example, here you have two balloons that have been rubbed together. They're identical balloons, latex balloons, and then they've been sprayed with toner particles that are positively charged. These are the pink regions here. And so you can see that this stuff charges pretty fast and pretty efficiently, but we don't really quite understand why this should happen. One model proposes that charging is actually driven by electrons, surface electrons that are in high energy states, unfavorable energy states, that then are able to relax to vacant low energy states on another surface when these two are brought together. And I won't get into the details of this, but one of the consequences of this model is that if you have asymmetric contact, meaning if you have a small surface rubbing against a large surface, such as a small particle rubbing against a large particle, what tends to happen is that the large particle becomes positively charged and the small one becomes negatively charged. And we see this all the time in experiments. So for example, this was some experiments some people did at University of Chicago where they had a bidisperse mixture of glass particles, and you can readily see this bimodal charging. Basically, the small ones become positively charged, or negatively charged, which is the blue peak here, and the large ones become positively charged, the red peak here. So just before I talk about the simulations, since there isn't really a model to describe tribocharging in homogeneous substances, we had to do some experiments to figure out how charging occurs in basically volcanic ash, or this chemically homogeneous silicate system. So we built this little fluidized apparatus where you have a bed of particles that are excited by a nitrogen flow. It comes in from the bottom. You create a little fountain, and particles collide. There are multiple collisions. And then this fountain passes through a ring electrode, which is connected to an electrometer. And you can measure the currents induced by these moving charged particles as they pass up and down through this ring electrode. And because particles are both positively and negatively charged, the average current is 0. But the standard deviation can be used to assess charging. So for example, if you take the standard deviation of this data, you get a nice charging curve here where you see the standard deviation increase very rapidly at the onset of the experiment, and then it levels off at some point, and basically at this point the system is fully saturated. So we wanted to explore how dynamics, basically how changing the energy of this fountain affects charging or affects the charging rates. And so we excited this bed of particles with different pressures, nitrogen flow pressures, and measured by fitting this equation to this data. You can extract a time constant, and we asked the question, okay, how does this time constant vary with driving pressure? And so these plots over here are for 3 different volcanic samples, and so you can see is that you make the pressure larger, the fountain becomes more energetic, you have more particle-particle collisions, and the time it takes for you to charge this material decreases. The second column shows the current as a function of driving pressure. So as you increase the driving pressure, you get more current induced in these rings, which is what we expect. So okay, this is cool, but the problem is that these charging rates are specific to the experimental apparatus. So it's very hard to take these charging rates and then translate them into, for example, a large-scale numerical model. So what we needed to do is create an intermediate model where we can translate these experiment-specific parameters to particle dynamics, basically trying to figure out collision rates in the fountain, granular temperatures, parameters that then we can import into a large-scale numerical model. So to do this, we use a code called MFIX. It's an open source multi-phase flow with interface exchange. There are two types. There are really two big flavors of MFIX. One is basically a two-fluid approach where particles are treated as interpenetrating fluids with separate momentum and energy equations. And it also, MFIX also supports DM, basically discrete element model coupled with fluid dynamics. So you track the individual particles Lagrangianly, and then the fluid phase is a Eulerian scheme, and his code is written in Fortran. So it's a fairly robust code. It's nice because unlike on some other DM packages that exist, MFIX already has the coupling between the fluid phase and the particle phase, so that was easy to use. It uses a soft sphere approach, meaning that when particles collide, the discrete particles collide, some overlap between particles is allowed, and it allows you to make the time step larger, and so your computation time goes down essentially. However, there's no support for electrostatics in the current version of MFIX DM, so we created two modules to simulate charging. One, which is this trapped electron model that I talked about previously, and then the second module includes electrostatic forces between dielectric particles. So for the charging model, it basically assumes that at the beginning of the simulation, each particle has an initial charge density of trapped electrons. And these are exchanged based on the overlap that the soft sphere model allows. So basically, when two particles overlap, you can calculate an effective area or contact area based on the radius and the overlap, this little delta here. And so the number of species or number of electrons transferred is then just the product of that contact area times the charge density on that particle times some scaling constant here, which is this C. And so I won't go into more of the detail, but it basically the charge on a given particle evolves something like this. It's basically the original number of trapped electrons minus those that have been lost, plus those that have been gained from other particles. The electrostatic force computation is a bit more complicated. I won't go into the details of what these equations mean, but I just sort of want to bring your attention to these two sort of brackets here. Basically, the first term in this equation is just your normal Coulomb force between 2 point sources, while the third and second term represent effects due to polarization. And these are important for especially dielectric materials that can be polarized, because you can actually get some pretty cool effects. So for example, even if you have particles that are charged to the same sign or basically carry the same sign charge, you would expect that they will always be repulsive. But because of these polarization effects, there are certain combinations of particle size and particle charge that produce net attractive forces when these particles are very close together. So this is what this plot shows here. Basically, at long distances, your particles are two positively charged particles have repulsive forces, but as you get close together, you get net attractive forces. So this in the model is actually what takes the longest time to compute in the loop. These sums take a good amount of time to compute. So for the simulations, we replicated the experimental apparatus with 100,000 particles in 2D. We were originally going to do it in full 3D, which would involve around 8 million particles, but the computation time became prohibitive, and we could probably get the same amount of information, or the information we need basically from a 2D model. So we went with that instead. And we have two classes of particles. So there are 100 micron particles and 200 micron particles, about 50% by volume each. We have a fluid grid that has a resolution of about 0.5 centimeters with some increased resolution here at the vent to replicate a very small nozzle. And for the soft particle implementation of the DM, we use a spring constant of 1,000. Simulations are run between 64 and 128 cores, and the runtime is usually between 2 and 3 weeks for a total simulation time of about 10 minutes, which is what we need to see that sort of charging profile that we see in the experiments. So here are just some validation runs. We basically to validate that the model was actually reproducing the dynamics we saw in the fountain. We compared both the height of the plume, or that little fountain, the numerical and the experimental one, for different pressures, and so we see that there's fairly good agreement. And we also compared the velocity distribution, the horizontal and vertical velocity distribution in both of the plumes, and so there's fairly good agreement. This is for the lowest energy case, so a bed pressure about 1.2 kilopascals. So these are some of the results from this model. So from this model, we can then now relate or translate these experiment-specific parameters, namely the bed pressure, to parameters that are more universally applicable to say, a large-scale model. So for example, here's the collision rate in the fountain as a function of bed pressure, as well as the collisional energy density in the fountain. This is sort of the evolution of the charging in the fountain. So we see, first of all, that large particles charge positively and the smaller ones charge negatively. And for a higher energy density, basically, you have more collisions, so the system charges faster. And for the lower energy case, the particles reach steady state at a slower rate. And here's basically what the distribution of charge looks like for the highest energy case. And again, we see sort of nice agreement with other experiments where you see the large particles charge positively and the small particles charge negatively. So at this point now, we have these constitutive relationships that we can put into a large-scale model that aren't experiment-specific. And so we again use MFIX, but instead of using the DM code, we now use the multi-phase fluid code, where we have basically our large-scale model that is approximately about 100 kilometers cubed, or in the order of. We can't obviously treat solids as individual particles. We have billions of particles, so each particle phase is assigned a different fluid phase, again described by different momentum and energy equations. And so using this approach, rather than having each particle have a specific property, basically particle properties are averaged across a grid cell. So this is a little movie of what the simulation, an initial simulation looks like. So we have a nozzle down here, basically a vent, and we allow this module to evolve, or this model to evolve, and we get a nice plume. What you see in this plot here is basically a plot of where we'd expect the positive charge to be. So because positive charge resides on heavier particles, most of it's concentrated at the vent or near the vent. These larger particles fall out of the plume before the smaller ones, and so this is something we would expect and has been inferred from measurements in the field as well. The model using about 512 processors, we have a resolution about 100 meters. So at this high resolution, we can start to resolve very small scale features like pyroclastic flows, or basically base surges, or horizontally moving density currents of ash that we weren't able to resolve previously. So that's pretty exciting. The one thing that I am working on at this point is refining the grid at the nozzle, or the vent, even further, because a lot of these lightning observations at the vent have scales that range between 1 meter to maybe 10 meters. So we really need sub-meter resolution at the vent at this point, but that's something that's still in progress at this point. Okay, so what am I doing for continuing work? Refining the large-scale plume model, but also integrating a fractal lightning model, so we can compute the electric field based on the charge distribution that we have over here, and then see if we can initiate lightning and see if that lightning's in the right place with respect to field measurements. Additionally, we're working on instrumentation that we intend to deploy at volcanoes to validate the large-scale model. So, for example, here we have a three-dimensional electrostatic field sensor that we can drop from a UAV into a plume. We go to a volcano in Mexico that erupts about 15 times a day, and it creates these sort of low energetic but charged plumes, and so that would be a good place to sort of validate this model at this point. So with that, I'll take any questions, and I'd like to thank the Blue Waters program Galen for his help, and Dr. Murray Binnage, a postdoc, who also helped me getting MFIX running.